Global stiffness matrix solving in Caesar. So application of boundary conditions. So boundary conditions like supports, anchors and restraints are considered by modifying the global stiffness matrix. Fixed supports and anchors, the corresponding degree of freedoms are set to zero displacements, because fixed support and anchor support means there is no displacement, no moment. So it means the displacement will be zero, and their rows and columns in the matrix are adjusted, mean deleted like that, based on the degree of freedom. Guides or spring supports introduce additional stiffnesses values in specific degree of freedom. Gaps and friction introduce non-linear relationship in the matrix for special conditions. Force displacement relationship. Once the global stiffness matrix K is constructed, it is used in the fundamental equation of structural analysis. K into X is equal to F, where K is the global stiffness matrix, X is the nodal displacement or rotation vector, which is unknown, we have to calculate it. Then F is the external force or moment vector, which is known in our case. We'll take the example and you will understand all these things. So solving the equations. To solve the displacement X, there are two steps. Numerical method. Caesar uses numerical solver like the Gaussian's eliminator to compute X, mean to calculate the X displacements. And second is iteration method. Iterative solution for non-linear problems. For system with non-linear effects like friction gap, solution is iterative. The metric is updated in each iteration to account for changing conditions until the convergence is achieved. You will see when the Caesar will run, it will solve the iteration and it will continue solving the iteration until it will converge. If it will not converge, it will show you the error, that non-convergence error. Element forces and moments. Using the displacement X, the software determines the internal forces and moments in each beam element or in each element of pipe. Number 2, software calculates the stresses, and these stress values are computed based on code specific formula that we already discussed. In process piping, we normally use B31.3 for axial, bending, torsional and combined stresses. And third step, reaction at the supports. So software calculates the reaction forces and moments at supports or anchor and derived from the displacements and stiffness relationship. After solving the displacements, the Caesar software calculates forces and moments in each element, stresses in each element, and reaction forces and moments at the boundary condition, means the supports. So what are the advantages for using the global stiffness matrix? Number 1, efficiency. The matrix method handles large complex piping system efficiently. Secondly, flexibility. It accommodates a wide range of boundary conditions and loading scenarios. Third, accuracy. It provides precise displacements, forces and stress values for compliance with the piping code. So these are the advantages. That's why we are using the global stiffness matrix in Caesar software. Let's walk through a simplified example to illustrate how Caesar assembles the global stiffness matrix and solve for displacements. Consider a straight pipe modeled as one beam element with two nodes, node 10, node 20. Node 10 anchor mean fixed supports, and node 20 is free end where an axial load is applied of 1000 kilonewton. So the maximum displacement will be due to this axial force. The pipe length is considered like 5 meter. OD of the pipe is 200 mm or 8 inch. Pipe wall thickness is 10 mm. Pipe material is carbon steel with Young's modulus E is equal to 2.88 10 to raise power 7 psi, and the rotations at the applied load will be theta z. Objective is we have to find out the axial displacement, which is dx, at node 20 by using the stiffness matrix approach. So here 10 to 20 is having an element E1 which is equal to 5 meter length, and this one element having two nodes, node 10 and node 20. So element stiffness matrix local coordinates. For a 1D beam element in 3D space, the stiffness matrix in local coordinate is derived based on beam theory. For simplicity, we consider only axial deflection, which is dx, and rotation theta z over here. So 2 by 2 stiffness matrix for one beam element is 1 0 0 1. Here you can see k into x is equal to f, where k is the stiffness and it is equal to EA over L. 1 0 0 1 is the matrix. So how it came? As we know, as per the Hooke's law, sigma is equal to E epsilon. And stress is directly proportional to strain with modulus of elasticity. We also know that sigma is equal to F over A, means stress is force per unit area. To put the value of sigma over here, F over A is equal to E into strain. Strain is, as we know, change in length over original length. So put it the value of strain delta L over L. So we can say that from this equation, F is equal to EA over L into change in length, where the change in length means the displacement. The whole matrix will be F is equal to K into X. So K is equal to EA over L, which is 1 0 0 1 in our case, and delta L is equal to X, which is X1 and X2, mean node 10 and node 20, and here is the force at node 10 and node 20. Let's input the value of force F at node 10 and node 20 and value of E, area A, length L, and find out the value of the displacement. K into X is equal to F, mean EA over L, 1 0 0 1, X1 X2, mean displacement at node 10, node 20, force at node 10, force at node 20 will be like this. So we have input the value of E, which is 2.88 into 10 to the power 7. Area A for in our case is 8-inch pipe, 5966, and length L is 5000 millimeters. So all these values having the same units. So 1 0 0 1, here at the node 10 there is no displacement because its anchor, the value is 0. So the only node is node 20, where we have to find out the displacement. X2 is equal to the force at node 10 is again 0 because it's fixed, and force at node 20 is 1000 kilonewton. Let's solve this equation and find out the value of X2. So after solving this, we found out 3.4 into 10 to the 7. X2 is equal to 1000 kilonewton, mean 10 to the power 3. 2 is equal to 0.03 millimeter. So this is how through this matrix we find out the displacement X at node 20. Element stiffness calculation after finding the displacement. So we have to calculate the axial stiffness. K axial is equal to EA over L. So after putting the value of E, A and L, so we found out the K axial is 3.4 into 10 to the 7 Newton per millimeter. Now bending stiffness, K bending, in our case bending is not applicable because the only force available in our case is axial force, but calculating the bending stiffness is 4 EI over L, where the value of E is 2.88 into 10 to the 7, I is pi by 64, DO raised to power 4 minus DI raised to power 4 divided by the total length. So in this way, the K bending, the bending stiffness is 6.22 into 10 to the power 11 Newton millimeter per radian. So rotational stiffness, the rotational stiffness depends on G and J, where G is equal to E over 2 into 1 plus nu. All these equations we already discussed in detail in part 2. So G is equal to 2.88 into 10 to the 7 divided by 2, 1 plus 0.3. So we consider nu as assumed as nu is equal to 0.3. So the value of G is 11.08 10 to the power 6 PA. So polar moment of inertia of pipe J is equal to pi by 32 DO, mean outer dia raised to power 4 minus inner dia raised to power 4, and the value comes out 5.4 into 10 to the power 7 millimeter raised to power 4. So the K rotation is equal to GJ over L, and after putting the value of G, which is this, value of J, which is this, and the length of the element, we find 11.9 into 10 to the power 10 Newton millimeter per radian is the rotational stiffness of the element. Let's take another example, and in this example it will illustrate how Caesar assembles the global stiffness matrix and solve for the displacements. The example is, consider a straight pipe modeled as two beam element with three nodes, node 10, node 20, node 30. It means the total length of the pipe is divided in two elements. So node 10 is anchor, which is fixed port. Node 20 is midpoint of the pipe, and node 30 is free and where the load will be applied. So total length of the pipe, let's consider 10 meter, and each element will be equal to 5 meter. The properties of the pipe we can consider like pipe OD 8 inch, which is 0.2 meter. Pipe thickness is 10 mm, which is 0.01 meter, and pipe material is carbon steel, and value of E, Young's modulus, is equal to 200 into 10 to raise power 9 Pascal. So element 1 is having length 5 meter. Element 2 is also having the length of 5 meter, because the whole length 10 meter is divided into two equal parts, and the load, a vertical downward force, which is Fy, is equal to 1000 Newton is applied at node 30. So bending moment at node 10 will be 10,000 Newton meter, which is equal to applied force 1000 multiplied by the distance from the fixed point. So theta z is equal to 10,000 Newton meter. Now the objective is we have to find out the vertical displacement, which is dy in our case at node 20 and 30, because here we have two elements. So in each element we have to find out the vertical displacement for the stiffness matrix approach. The element stiffness matrix local coordinates for a 1D beam elements in 3D space, the stiffness matrix in local coordinates is derived based on beam theory. For simplicity, we consider only the vertical deflection, which is dy, and rotation theta z here. So 4x4 stiffness matrix for a beam element is Ke is equal to Ei over L cube, and you can see the complete composition of this matrix. Let's solve and put the values of E is equal to 200 into 10 to the power 9 pascals. L1, the length of the one element, is 5 meter, and let's compute the stiffness matrix for each element of the pipe, where E is the modulus of elasticity as we discussed earlier, I is the moment of inertia of the pipe. In our case, I is equal to pi by 64, outer dia raised to power 4 minus inner dia raised to power 4, and this thing we already discussed in part 2. The L is the length of the element. In our case, there are two elements and each element is having a length of 5 meters. For our pipe, I is equal to pi by 64, 0.2 raised to power 4 minus 0.18 raised to power 4 is equal to 2.7 into 10 to raised to power minus 5 meter raised to power 4. For a pipe system, the local stiffness matrix includes axial, bending, and rotational effect. The stiffness matrix Ke for a single pipe element, when there are two elements, for single pipe element is expressed as Ke is equal to K11, K12, K21, K22. This is the stiffness matrix for one element. Similar stiffness matrix will be for the second element. So where Ke are 6 by 6 sub-matrix that includes axial, bending, and rotation, mean 2 plus 2 plus 2. So it will be 6 by 6 sub-matrix that includes axial, bending, and rotation. So let's calculate K axial. Again, same formula, E over L, substituting the values of E and A over L. So we got the K axial is equal to 3.04 into 10 to raise power 8 Newton per meter. Bending stiffness, K bending, is equal to 4 EI over L. Substituting the value of EI and L, so we got the K bending value is, bending stiffness value is equal to 4.32 into 10 to the power 6 Newton meter per rate. Rotational stiffness, the rotational stiffness depends again on G and J both. So first calculate the G. The value of G is equal to E over 2 1 plus into nu. Nu again we can assume 0.3. So value of G after substituting the values of E and nu is 76.92 10 to the power 9 Pascal. Polar moment of inertia of pipe, which is equal to J, is equal to pi by 32. Outer diameter of the pipe raised to power 4 minus inner diameter of the pipe raised to power 4, and after substituting the values of DO and DI, we got polar moment of inertia of the pipe is 5.4 into 10 to the power minus 5 meter raised to power 4. So K rotation is J G over L. After substituting the values of J, G, and L, so it comes out as 8.3 into 10 to the power 5 Newton meter per radian.